So hello, everyone. This is a module that's dedicated for the people evolving within the neocardial lab structure. We will be going through some of the principle regarding 3D echo and measurements using the TomTEC packages. So I will be opening the TomTEC package. This is the TomTEC Arena, and then here we have our study patient. So we will be opening this patient. And we will going through some of the 3D evaluations of both the LV and the RV using the TomTEC packages. So first of all, when we open the study, we can see that the study is getting loaded here, 58 on 133. On the panel here, you have the zones for the typical measurements of conventional echo markers. And then we will be going through the 3D. So here are the thumbnails as it's loading. And we can see that some of the 3D are appearing here. And we might go through different types of 3Ds. So now that the whole study has loaded, we can start looking at some of the images that's there. And you can already see that here I have loaded some of the 3D. And if I open, for example, I'm going to be concentrating on an LV. So here from this view, you can see from the thumbnail that it says full volume, 3D beats HVRQ, which means that it's a high volume rate capture that's been done. So it's based on a 1 cardiac cycle, and it uses the X matrix probe to be sending ultrasound beams in various directions so that it can capture as much as possible a volume with high frame rate. And so you can see that on the top left of the thumbnail, it says that it's using the X7.2 probe, and it tells you that it's at 40 Hertz, which is the frame rate of capture. And what you want to make sure is that you can see all the walls of your LV so that you can really capture the endocardial border and make sure that we have a good volume estimates. So here, these are HRVs. And there is also here another one that tells you that it's a 3D beats 4Q, which means that it actually had to stitch 4 cardiac cycles to get a volume. And you can see that this one is actually at 35 Hertz, so a bit less of a frame rate. Typically, using the multi-beat method will give you more granular architectural information. So it's good for valves, and it's good to look at some of the anatomy, but it might not be as reliable for an assessment of a volume, which might change slightly depending on the loading condition from one cardiac cycle to another. So what we'll start with one of our HRVs, and by right-clicking, so first of all, by double-clicking on this, I can zoom, and I can see my 3D volume. So I can see my LV here that is inverted. And I can see that if I start moving my different axes, depending on the line of movement, I can see my 3D structure kind of appearing in different planes as I'm going up and down, and as I'm going left to right, and as I am also going in a diagonal fashion. So it's just to show that the image has captured a full 3D volume. So what we'll be interested is by looking first at the LV analysis package. So the LV analysis package by TomTEC has already been pre-engineered to try to do as much as possible the tracking automatically. But dealing with small newborns, we might need to actually do some adjustments to make sure that the trackings are okay. So you can see that has done a lot of the calculation, but we'll go back to some of the elements it has done. So here you can see from a 1 to 5 step point, it tells you exactly what you should be marking for the actual evaluation. So it tells you that you should be at the apex and the mitral valve. Same thing, you want to be at the apex and the mitral valve of your 2-chamber view. And this is your 3-chamber view, apex, mitral valve. So apex mitral valve, apex mitral valve, apex mitral valve. Here it acts, you can see for apex. So we are at the apex. And then from here, you can also use it to turn and look at the different views from the 3D, but that's not what we're interested in. The timing of definitions will allow you to identify the end of diastole and end of systole. So you can choose to change, let's say that you don't believe that this is end of diastole or end of systole. You can adjust based on your M mode. And then you can go into the LV tracking revision. So on this panel, this where we're going to be seeing the end diastole, the end systole, or the end diastole and end systole. So you can see already that there's probably some work to do here. So by clicking on the yellow box, you would be able to adjust things according to the tracking of your endocardial layer. So what you want to do is to identify the different layer. So this is for systole. So clearly you want to track the endocardial areas as much as possible. And this is end of diastole. So it's a bit like doing your Simpsons, where you want to go and identify as much as possible all your areas. And you want to do this in all the views. Same thing here. So here it's good. So you can see the wall here. And you can see that this is your aortic valve. And this seems okay. Same thing in diastole. This looks like it's encompassing the entire wall, so that looks fine. And then you can actually look at, does this make sense? So you can pause it and go on a frame by frame basis. And you can see that probably what you identified here is not the exact right apical area. And now probably it looks like it's tracking more appropriately. Same thing here. It looks okay. And that looks fine also. And so what you can do is that if you go back to the D, you can even choose the different layers and adjust on a plane by plane in this area. So here, probably we would go here. This looks okay. And as you're going to the different section, you want to make sure that it has identified, and that's at the end of diastole. And you can do the same at the end of systole. And you can see the wall here. Now, once you're satisfied with your tracking, you can go in the analysis stage. And within your analysis stage, first you see your global volume as a rendering from your 3D echo. And then you get the estimates of your interest. So you have the end diastolic volume and the end systolic volume, which this minus this gives you a stroke volume. And if you do an ejection fraction, which is the end diastolic volume minus the end systolic volume divided by the end diastolic volume, it gives you an EF of 62.3%. You have a global longitudinal strain, which means that the actual strain on the longitudinal component is at minus 22.3%. And the circumferential strain, which is at the level of the mid-papillary muscle, is at around minus 32.3%. You have your twist and your torsion, which means that it's normalized to the length. So the twist is really the rotation from the base to the apex of how many degrees there is of rotation of gradient between these two elements. So then on the other panel, you can start seeing a bit more information. So first of all, if you hover over the different elements, it will tell you, for example, the longitudinal strain, what are the different segments, and you can see if there's areas that are actually peaking before other areas. So you've identified that the peak of your systole is here, and you can see that actually most of your segments, which are identified in the different zones, are peaking in the appropriate areas. You can do the same thing with your circumferential strain, which is there. So you can have all the different segments. And you can even look at the time to peak in milliseconds. So the time to get to basically your end systole. Then this is displacement is the actual linear movement. So what's the distance that it actually moved? So you can look at the circumferential displacement towards the inside. You can look at the radial displacement. You can look at the longitudinal one, and then you can look at the degrees, which mean the rotation that it has. And basically, you have your apical rotation. You have your twist, which is typically your apical minus your basal. So that's why this one is higher, because this is a positive value minus a negative value. So this is your basal. And then you have your twist at the end of systole, which is 4.9 degrees. Sorry, it's here. The peak of the twist is 4.9 degrees. It gives you the peak. And then you have global volumes. So this shows you as the ventricle is contracting, the volume that it contains. And then the segmental volumes of each representative area of the ventricle. So this is a lot of data, but obviously when we're doing research, we have to select those that we think are of most interest. You can see here that there's no mass. And one of the reasons there's no mass is because once we've done the actual tracking, we didn't tell the TomTEC software the myocardial areas. So you could choose to add the myocardial layer. But for that, you can see that we're missing part of the wall here and in here. So you would really need to have a 3D capture that contains the entire wall. But if you do have, then you can get an estimate of your mass, which here would be 3 grams of muscle mass. So this is how to do an LV. So we'll open another one, and then we'll retry from the beginning. So this patient has 171 clips. It's opening progressively. And we're going to again go to the 3D ones. And then we're going to see the difference. So as it's loading, we're going to also show how to do the RV, which is a bit less automated than the LV. Okay, so same thing. You can see here, this is an HVR, this is an HVR, this is a 4-beat capture. This is a 4-beat capture. So we're going to try this with a 4-beat capture to start with. The software is processing the images. You can see already that there's some issues where it's identified the apex. So we're going to go back to the adjustment. The apex is here. The mitral valve is here. Apex is here. Mitral valve is here. Apex is here. And this is a kid who has quite significant LV dilation. You can see in 3D kind of the LV cavity. And the reason is because this baby has a significant ductus with left-to-right shunting. So this is just to give you kind of a map-see. So you can see the peak of diastole and the peak of systole. You can also do it with kind of the septal areas to see how the contraction of the septum happens. So then again, we would need to define our different LV structures. Can add a wall. You can see that the mitral valve is a bit lower actually. At the end of systole, it's also much lower. And this is end of systole. Here. And the systole is here. So there is a lot of troubleshooting to be done in certain of these images. Sometimes it's going to track right away from the get-go. And then we'll finish here. And then we have a rendering of this LV. So you can see this baby has a very high ejection fraction, probably because it's compensating for that ductus arteriosus. You have the twist, the circumferential strain, longitudinal strain here, and the mass. And you can look at the degrees. You can see the twist. So the peak twist is at 5.8. And the torsion means this divided by the length in centimeters. So that's why it gives you 2.5 degrees by centimeters, normalized for the length of that LV. So we've done the LV. We'll go with an RV view. So we'll try to identify a view that outlines the RV, hopefully. And then we'll try to use this one. So the RV is not automated. There's no, there has not been any engineering behind it to automate it. And it's highly based on also your views of the LV. So it's not typical that we have any of the LV views, but you can see that it's asking you to do an apex of an LV. You can see here that we don't have the apex of the LV because we concentrated on the RV. And then you want to find your this is the AV aortic valve. And then you do the same thing, but on the RV compartment side, which is the one that we're interested in. So apex RV, apex tricuspid valve. And then it tells you here that you need to book your two junctions. So we have our two junctions. And where's your RV wall? So you can see how we might be losing really a small portion of the RV here. You can even change your brightness if you don't think you're seeing well. And then we go into the butyl revisions. So butyl revisions, first of all, is the same thing. You want to go on a step-by-step to identify the end diastole of your RV. And then here it's asking you to put the hinge points of your tricuspid valve. Okay. And then you can do some tracking revisions. So now it's going to calculate to find the end systole. And then you're going to want to do the same revisions. So end diastole is here, and systole is here. Again, you can increase your brightness and contrast. Same thing here. This is your outflow track. And then this is kind of the 4-chamber view. And you can see how you can go down in the cavity and diastole and systole, and then go down further. This looks okay, but this probably should be more like this. And as you're going further, you can readjust because this doesn't make any sense. So you would have to probably readjust some of the elements here. And eventually, as you're going from layer to layer, you can adjust things. And then from here, what you can do is also turn to outline your outflow track. And then do the same in both systole and diastole. The system is still so now we're at the analysis stage. And you can check where is your RV standing compared to your 3D. And you can see your RV in the 3D plane. And then from there, you get an ejection fraction, a stroke volume, and diastolic volume and systolic volume. And then this will give you a manual 2D assessment. So it will calculate for you the TAPSE, the fractional error change, the longitudinal strain from the septum and the free wall. It will give you the measurements, the diameters at the base, the mid cavity, and at the level of the length. You can redo some manual measurements from here. You have the measurement tools here. So let's say you want to do like an FAC or a TAPSE. You could do it from here. And then calculate certain aspects. So these are the elements that we would be interested in, mostly the ejection fraction of this RV for the 3D measurements. So I hope that was able to give you some sense of the information that you're able to obtain from 3D volumes for RV and LV function. And this is not meant for assessment of structural anomalies, but really for functional anomalies.